Tonight, we're going to follow two machines that were never meant to travel this far. They left Earth in 1977, built for 5 years of work and for 2 planets. They are still sending data almost 50 years later, from a distance where their signals need nearly a full day to arrive. And when they finally reached the outer wall of the Sun's territory, nothing there matched what had been predicted. The boundary sat billions of miles past every model. The shape made no sense. The magnetic field refused to turn. And the space on the far side was never empty at all. 7 discoveries that showed how little we understood the place we live in. Before this night is over, you'll know how 2 probes built from 1970s parts located the true limit of the Sun's reach, and why nothing beyond it behaved the way anyone expected. Before we start, if the deep sky keeps you curious the way it keeps us curious, take a moment to like this video or to subscribe. It costs you nothing, and it helps this channel find more people who wonder about the same things. Let's begin. In the summer of 1977, Florida is heavy with heat. Cape Canaveral sits at the edge of the water, flat and bright and salted. The air outside smells of salt and hot metal. Inside a clean room, 2 machines are being finished. They are almost identical, built from the same drawings by the same hands. They will be called Voyager 1 and Voyager 2. For now, they are hardware, nothing more. Aluminum booms, folded in tight against the body, a wide white dish, pale under the lights. Cables bundled and taped by hand, each one labeled and traced. Technicians in white coveralls move around them. Nothing is hurried. A dropped tool is a delay of weeks, so nothing is dropped. The room is kept cooler than the coast outside. The air is filtered until it carries almost nothing. Every part that goes into these 2 machines has been inspected, logged, and inspected again by a second person who signs for it. The 2 are close enough to identical that a component built for one would fit the other without complaint. The paperwork still records which serial number went into which body, because someone will want to know. The mission on paper is modest. 5 years, Jupiter, then Saturn, and nothing beyond that in writing. The contracts assume it. The schedules assume it. The engineers know that number is a floor and not a ceiling. But the number that actually matters is not written in years. It is written in watts. Every instrument, every heater, every radio transmission will be paid for out of one supply. Each spacecraft carries radioisotope thermoelectric generators. Inside them is plutonium, and the plutonium is warm. It is warm because it is decaying. That is all a radioisotope generator does. It holds a material that falls apart, and it catches the heat that falling apart releases. The heat crosses a bank of thermocouples. The thermocouples turn a temperature difference into a steady current. There is no valve and no throttle in the arrangement, only heat arriving and a fraction of it leaving as electricity. There are no moving parts, nothing spins, nothing burns. There is only the slow arithmetic of decay. The amount of plutonium loaded into those generators is fixed on launch day. Once the fairing closes, nothing more goes in. There is no refueling and no resupply. Not ever. And the rate at which those atoms come apart is known in advance. It is a curve, and physicists could draw it in 1977 on a single sheet of paper with nothing but the half-life. They could name any year and read the number off the page. That is an unusual thing to have. Most machines fail in ways nobody can schedule. A bearing wears, a seal cracks, a circuit gives out on a day nobody predicted, and the failure is a surprise. These 2 will lose their power supply on a timetable printed before they left the ground. The generators drop roughly 4 watts every year. 4 watts is a small number. A nightlight uses more. But 4 watts taken every year forever is a countdown rather than an expense. Each year the engineers will have less to spend than the year before, so the list of things worth powering will have to get shorter, one item at a time. Heaters keep fluid lines from freezing solid in the cold. A transmitter has to stay strong enough to be heard across a distance that keeps growing. Instruments want current whenever they are asked to look at something. All of it comes out of the same falling number. So the sealing of the fairing in 1977 is 2 things at once. It is the beginning of a mission, and it is the setting of a date of death. Nobody at Cape Canaveral says it in those words. The term used is power margin. The phrase in the documents is end of mission. Everyone building the spacecraft understands what the phrase covers. They talk about it the way people talk about weather they cannot change. And then they do something quietly stubborn about it. They build to the 5-year requirement, and then they choose parts that will age well past it. There is a cheaper capacitor and a better one, and for a 5-year mission, the cheaper one is defensible, and they take the better one. They add redundancy where the requirement does not ask for any. They are building an object that will never again be touched by human hands, and every choice made in that room is permanent. That knowledge changes the way a person tightens a bolt. Voyager 2 launches first on the 20th of August 1977. The morning is clear. The engines light, and the sound arrives a few seconds later, across the water, as a low pressure in the chest. The vehicle lifts on a column of white smoke that leans away from the pad in the sea wind. The rocket climbs, tips east over the Atlantic, and is gone. Nobody sees it again. By the time the smoke clears, the spacecraft is on a path that nobody standing here can correct. The pad cools. The generators are already a day older than they were at sunrise. 16 days pass. On the 5th of September, Voyager 1 launches from the same stretch of coast. It is the second launch of the pair, and it carries the number 1. The naming looks like an error. It is not. Voyager 1 is placed on a faster trajectory, a shorter arc through the same part of the sky. It will reach Jupiter before its twin. It will arrive first at every destination the 2 of them share. So the numbering follows arrival rather than departure. 2 launches, 16 days apart, from 1 pair of pads. In a summer most people remember for other reasons. From here on, the spacecraft are known only through numbers, voltages, temperatures, counts of particles, all of it arriving as a thin stream of telemetry. An engineer at a desk reads a column of figures and decides, on that basis alone, whether the machine is well. The signal leaves the dish out there and arrives here faint enough to be pulled out of the noise. Nothing else comes back. No photograph of the spacecraft itself, no view of its own hull. It reports on the sky around it and on its own interior, and never on its own outside. A figure that falls outside its expected range is the only symptom anyone will ever get. The cause has to be reasoned out from the ground, from a table of numbers, by people who will never see the fault. 3 years later, the first thing breaks. In 1980, the plasma detector aboard Voyager 1 fails. An instrument built to measure the thin wind of charged particles between the planets stops returning useful data. Commands are sent to it anyway, in the order the procedure calls for, and the instrument does not answer. The mission has other instruments, and the science plan absorbs the gap. The spacecraft is not yet 3 years old. Already it is a slightly different machine than the one that left Florida. Nobody can go up and look at it. Nobody can open a panel, trace the fault, and close the panel again. No one ever will. The instrument is logged as lost, the plan is rewritten around it, and the work continues with what is left. Not one dramatic failure then, but a long series of small subtractions. A detector goes, then a heater somewhere else. Then a channel that used to carry data carries nothing. And underneath all of it, the power available keeps narrowing. The 5-year mission is delivered as promised, Jupiter and Saturn both. Everything after that is time the engineers bought in advance, in a clean room, with decisions nobody asked them to make. The spacecraft do not know any of this. They have no sense of duration. There is no counter aboard either one that reads how long it has been out there, and no instrument that would care. They will keep doing exactly what they were told to do until there is not enough power left to do it. They execute stored commands. They hold their heaters on. They point their dish back toward a pale star that is the sun. The mission begins as a line drawn on paper. 2 spacecraft, a short list of planets, and 1 arrangement of worlds that will not come back around for a very long time. The outer planets have drifted into a curve that lets a single ship touch them one after another. Each world lends a little of its own motion to the ship that passes close by. The ship gains speed and the planet loses almost nothing. It works only if the ships leave inside a narrow window. It works only if nothing else is asked of them along the way. Every extra request costs a planet. A few extra hours spent beside one moon can pull the ship off the angle the next planet needs. The next planet does not wait. The people who plan this understand that from the beginning. They work it out curve by curve, trading a few days of launch against a few degrees of approach. They stop when the numbers stop fighting. They draw the long road first. Jupiter, then Saturn, then Uranus, then Neptune. 4 worlds in one thread. No spacecraft has ever done such a thing. None has ever been asked to stay awake long enough to try. Each planet on the list is only a doorway to the next one. Miss the angle at one of them, and everything past it becomes unreachable. It does not matter how well the ship is still working when it gets there. And then a second idea starts pulling at the first. Saturn has a moon wrapped in air. Titan is not a bare ball of ice like the others. Something soft and orange sits over its surface and hides it completely. Earlier missions could only tell that the haze was there, thick enough to swallow the light and hold it. That is either a nuisance or the most interesting thing in the outer solar system, depending on who is asked. A moon with an atmosphere is not a small thing. There are very few of them anywhere in the Sun's family. Titan is large. Nobody knows how deep this one goes. Nobody knows what is under it. Everything anyone has is a small orange disk seen from very far away. Titan may hold a chemistry that resembles a much younger Earth. Cold, thick, patient, unfinished. And it sits right there, in the path already planned, tucked close to Saturn. Taking it looks easy on a map. The planners know almost at once what it would really cost. To study Titan properly, a spacecraft cannot simply glance at it in passing. It has to slide behind the moon as seen from Earth. For a few minutes, the moon has to stand directly between the ship and home. The radio then crosses the orange air on its way back. The tone that returns is not quite the tone that left. The signal bends and slows as it passes through, layer by layer. That small change is the measurement. It gives density and temperature and the shape of an atmosphere nobody has ever sounded. The whole result depends on a few minutes of geometry. The ship has to be in one narrow place at one exact time. Everything about the pass has to be right long before it happens. There is no second attempt at a moon a ship crosses only once. But that geometry is not free. Titan orbits well away from Saturn's cloud tops. To reach the right point behind it, the spacecraft has to come in on one particular angle. Once it does, Saturn takes hold of it. The planet's gravity does not just bend the path sideways, it lifts it. Whatever leaves Saturn on that trajectory is thrown north, out of the flat sheet the planets travel in. There is no way back down from there. Nothing the spacecraft carries can turn a path like that around. Once the encounter is over, the road is fixed. Uranus and Neptune fall off the list, years before anyone could have reached them. So the plan is split in two. Voyager 1 is given Titan. Voyager 2 is given the distance. That is the trade. The second ship keeps the long road and stays low, still in reach of the ice giants. The names are misleading, and they have confused people ever since. Voyager 2 leaves Earth first. Voyager 1 leaves later, on a faster arc, and passes it somewhere in the dark between the worlds. It reaches Jupiter first. That is why it carries the number 1. Not seniority, but arrival. The numbers record the order of the encounters, rather than the order of the launches. 2 ships on 2 roads, built from the same drawings, carrying nearly the same instruments, the same radios, tuned to the same faint band. For a while they behave almost like twins. They cross the asteroid belt. They meet Jupiter and find it more alive than anyone expects. They leave it faster than they came. Voyager 1 reaches Saturn first, and there the 2 roads separate for good. It goes for the moon. Titan comes before the planet, not after it. The spacecraft swings past the moon first, close, and puts it between itself and Earth. The signal threads the orange air on the way out. It returns a description of a sky nobody has ever stood under. The measurement works. Only then does the ship come in over Saturn itself. The aim point was chosen long in advance. Once the ship is committed to it, the planet does the rest of the work. Without consulting anyone, the planet takes the path and lifts it, exactly as the numbers said it would. The spacecraft is no longer traveling with the planets. Below it, the solar system flattens into a plate it is leaving behind. There is nothing ahead on that heading. No planet, no moon, no scheduled encounter for the rest of its working life. Just a rising line into empty sky. Voyager 2 is nowhere near any of this. It cannot be. It is still months out from Saturn, low and slow, crossing the gap on the long road. Its course carries a quiet condition. If Voyager 1 fails at Titan, Voyager 2 will be turned toward the moon to try the same measurement again. That would cost the second ship the far planets too. The tour would end at Saturn for both of them. A backup written into a flight plan is a promise to throw away half the mission if the first ship comes back with nothing. So the second ship travels for years with its future written as a condition, waiting on a measurement it will not be present for. It flies as a spare and a scout at once. Its instructions take effect only if something goes wrong far ahead of it. The measurement succeeds, so Voyager 2 is released to continue. It keeps the line the planners drew years earlier. It arrives at Saturn long after the first ship has gone. By then, Voyager 1 is far above, out of the sunlit lane the planets keep to. Voyager 2 passes low instead, and each further encounter nudges it a little the other way. Southward, 2 ships built in the same room, now traveling in different skies. The cost of Titan is counted in planets, and it is paid on purpose. What nobody weighs is the shape that choice will give the mission afterward. The arguments are about atmospheres and rings and moons. They are about what a camera can return in the few hours a flyby allows. They are about how much a single close passage can be made to carry. The choice is made for the moon. Everything else that comes out of it comes out sideways. A geometry chosen for a few hours of radio decides everything that follows. Voyager 2 keeps to the flat lane, with its list of planets still intact. The sun gives off light, and it also gives off something heavier. A thin stream of particles lifts away from its outer layers and never comes back. It is called the solar wind. It is not wind in the way you know wind. There is no air for it to push. It is matter itself, moving outward, forever, The sun has been letting go of itself this way for as long as it has been shining. The sun does not aim it. It goes out in every direction at once, above the poles and along the middle, in front of the planets and behind them. It is not equally strong in every direction, but there is no direction it leaves alone. A steady exhale with no chest behind it. The wind is fast, faster than anything ever built to fly, and nothing out there is arranged to slow it down. Past the outermost planets there is nothing left to turn it aside, and nothing left that it has to go around. The wind runs on into the dark, spreading the same amount of matter across a wider and wider shell with every year it travels. It weakens. It does not stop. And something is waiting for it. The space between the stars is not empty. It is close to empty, but not empty. There is gas out there, and dust, and a faint pressure of its own. It has been there far longer than the sun. The gas between the stars was not made by the sun, and does not answer to it. It drifts slowly in its own direction, and it was drifting that way long before the planets had cooled. The solar wind is blowing into it. For a very long stretch, the wind wins. It is strong near the sun, and it clears everything ahead of it. It holds the interstellar gas off, and keeps it there. Farther out, where the wind is thinner, that grip loosens. Somewhere in that thinning, the two pressures come even. The wind pushing out, the galaxy pushing in. At that line, the wind stops being a wind. It piles up. It slows, turns, and begins to move sideways along a wall it cannot cross. The wall is not a thing you could touch, only a place where one pressure gives out and another takes over. Everything inside that wall is a cavity, a hollow the sun has blown for itself in the gas between the stars. The sun has been blowing it since long before there were oceans on Earth. That cavity has a name: the heliosphere, a bubble. Everything you have ever known is inside it. Every planet, every moon, every comet that has ever come around, every rock in every belt, every human being who has ever lived has spent that whole life inside the same bubble of solar wind. It is held open by pressure and by nothing else. The wind is not steady, and the sun rises and falls on a cycle of about 11 years. So the wall it holds up breathes with it. The bubble moves. The sun is traveling through the galaxy, and it carries its bubble with it. The front of it presses forward. The back of it trails away, drawn out and soft, the way a wake spreads and fades behind a slow boat. The wall in front is not the same as the wall behind. One is being run into. The other is only being left. None of that shape has ever been seen from outside, because standing outside it has never once been possible for anyone or anything we have built. The shape is not a photograph, but a drawing made out of arithmetic, assembled from readings taken by instruments that were themselves inside it. You cannot see the walls of a room by lying on the floor of it. You can only feel your way. Instruments felt the wind as it passed, and reported what passed. Speed here, direction here. The wind at this spot, on this day, going this way. One moving point in an enormous volume, and everything past it had to be reasoned outward from a single thread of readings. The thread was thin, and the space around it kept opening in every direction. That is the position astronomy was in. The bubble was known to exist. Its size was not known at all. Before Voyager, the largest serious estimate of how far the wind reached was 3 times the smallest. Both numbers came from careful people with careful reasoning, and both had been published. Either one could be defended in a room full of experts. The range was not a sign of carelessness. It was what honest arithmetic produced when the inputs were unknown. The distance to the edge of our own bubble was written down as a range, not as a number. You could not say where you lived. You could only say between which two walls you probably lived. The models disagreed, because the models were built on assumptions. Assumptions about how thick the wind stayed as it spread. Assumptions about how hard the galaxy pushed back. Assumptions about whether the boundary held still, or moved in and out as the sun grew louder and quieter. Change one assumption, and the answer moved by a factor you could not ignore. And no measurement from Earth could decide between them. Each model agreed with everything anyone could see from here. Which is why seeing from here was not enough. Light from distant stars passes through the boundary, but it does not report on the crossing. The gas out there is too thin to glow in any way that would settle the question. The wind at Earth tells you about the wind at Earth. It tells you almost nothing about what the wind does after it has stopped mattering to us. There was no experiment to run. No version of the heliosphere could be built small and watched from outside. And nothing of the kind could be carried into a laboratory and tested. The subject was larger than everything, and it refused to be looked at. Something had to go out and be there when the wind ended. It had to keep listening the whole way out. There would be nothing to photograph. A boundary in near vacuum has no surface to reflect anything. It would announce itself only as a change in the numbers. The wind would fall off, something else would rise. And the only way to know it had happened was to be there while it happened. Not near it, in it. Until 2012, no instrument had ever been on the far side of that wall. Everything said about the edge was careful inference, each layer resting on the one under it, and none of them resting on the ground. The strange part is how ordinary that is. At this scale, we have detailed maps of the surfaces of moons no one will ever stand on. We have counted the storms of planets that would kill anything we sent into them. We have weighed stars we will never approach, and the size of the space we ourselves live inside stayed a range in a textbook. The bubble is not overhead, the way weather is. It is not somewhere you could travel to and look at. It is the condition of every measurement ever made, including the ones made to find its edge. The argument about that edge was still running when two spacecraft were already moving toward the answer. They had not been sent for it. They had been built for the planets, and the boundary was something they might reach afterward, if their instruments were still alive by then. Nobody had promised that they would be. They went outward all the same, carrying their instruments toward the part of the bubble no model could settle. The solar wind leaves the sun very fast. It is a thin stream of charged particles, mostly protons and electrons. It moves outward in every direction at once, and nothing in the space between the planets is thick enough to hold it back. It sweeps past them without slowing in any way you could measure. It carries the sun's magnetic field with it, stretched and wound into a long spiral. That wind is what makes the bubble. It blows outward until it can no longer push. And where it stops, the bubble ends. But it does not stop all at once. Before it stops, it has to slow down. And in space, slowing down is not gentle. Sound needs something to travel through. In the thin gas between the planets, there is something to carry a wave. Barely. There are scattered particles out there, and a magnetic field threaded through them. And that is enough to pass a disturbance from one place to the next. The speed of that disturbance is the local speed of sound, and the solar wind is faster than it. The wind is supersonic. It has been supersonic since it left the corona. A supersonic flow cannot feel what lies ahead of it. The news of an obstacle travels at the speed of sound, and the flow outruns the news. So it arrives without warning. And when it finally meets resistance, it does not curve politely around it. It piles up. That pile-up is a shock. You know the shape of this from air. A jet crossing the sound barrier drags a cone of compressed air behind it. The change is not gradual. There is a thin surface where the pressure jumps, and the gas on either side behaves differently. The same thing happens at the outer edge of the solar wind, only it is far larger there and far slower to cross. The surface where the wind first slows is called the termination shock. It is the inner wall of the boundary region. Beyond it, the wind is still there, still moving outward. But it is no longer supersonic. It has been beaten down. For decades, nobody knew where that surface was. Estimates ranged widely, and they kept moving as the sun grew louder and quieter. Some put the wall much closer in, and some put it much farther out. The only way to settle it was to go there and cross it. In December 2004, Voyager 1 reaches it. The spacecraft is 94 astronomical units out, 94 times the distance between the Sun and the Earth. There is no image of the crossing. The instruments that would have looked at it had been dark for years. What the spacecraft carries instead is a magnetometer and a set of detectors that count particles, and those are enough to describe what happens. The magnetic field is the first thing that speaks. Out in the ordinary solar wind, that field is faint, a whisper stretched thin by distance. Then it rises, and it rises quickly. It roughly triples, the way a line jumps rather than climbs. That tripling is the signature. When a flow slows abruptly, the magnetic field lines frozen into it are pushed together. They cannot slide past one another, so they stack, and the field strengthens. The wind has been squeezed. At the same time, the speed of the flow drops away. The wind that arrives fast leaves the shock much slower than it came. And the energy of that lost motion does not disappear. It goes into heat. The gas beyond the shock is hotter than the gas before it, by a great deal. This is what a shock does. It takes ordered motion and turns it into disorder. Speed becomes temperature. The calm outward march becomes a slow, hot, churning drift. The particle detectors have something to say about the crossing as well. Charged particles get caught in the compressed field and thrown back and forth across it, and some of them gain a little energy on every pass. The counters climb. Voyager 1 crosses that surface once and keeps going. It is now inside a region no spacecraft had ever entered. The wind around it still comes from the sun, but it is subsonic now, and it can feel what lies ahead. It begins to turn. 3 years pass. On the far side of the solar system, a second spacecraft approaches. Voyager 2 is heading south, well below the plane of the planets, on a path very different from the first one. It has been falling outward since the year it left Earth, unpowered, carried by nothing but the speed it was given at launch. Between the 30th of August and the 1st of September 2007, it crosses. The same signatures arrive in the same order. The field jumps. The flow slows. The gas heats. But the distance is wrong. Voyager 2 crosses at 84 astronomical units. Voyager 1 crossed at 94. 10 astronomical units separate two crossings of what was supposed to be a single surface. If the bubble were a sphere, both spacecraft would have found the wall at the same depth. They did not find it at the same depth. So the bubble is not a sphere. Part of the difference is time. The sun's output rises and falls in a slow cycle, and the pressure of the wind rises and falls with it. When the wind weakens, the wall drifts inward. When it strengthens, the wall is pushed back out again. The boundary is not fixed in place. It moves in and out over years, the way a chest moves. But that breathing alone does not account for the gap between the two crossings. Voyager 1 left the solar system heading north, and Voyager 2 heading south. Their crossings are not two samples of the same place at different moments. They are two samples of different parts of a lopsided object. The boundary sits roughly 7 astronomical units closer to the Sun in the south than it does on the other side. Something is pressing on the underside of the bubble. The pressure on it is not the same in every direction. The Sun does not sit still in the galaxy. It moves, and the gas between the stars moves, and the two of them do not move at the same speed or in the same direction. There is a relative wind out there then, thin beyond imagining, and it leans constantly against the outside of the bubble. Where it leans hardest, the bubble is pushed in. The wall arrives sooner in that direction because it has been driven closer to the Sun. That is what the two crossings describe, though nobody has seen it. One measurement would have given a number. 2 measurements gave a shape instead. And the shape is not the clean sphere that the old diagrams used to draw. It is a bubble with a dent in its lower flank, held open by a wind from inside and pressed by another from outside. Somewhere in that uneven surface, the solar wind slows for the last time. The two spacecraft crossed it years apart, at different depths. Neither one felt anything. The shock is real, but it is spread across an enormous stretch of nearly empty space. There is nothing out there to shudder against. The instruments simply reported new values, and the new values held. By the time anyone on Earth read them, both crossings were finished. Beyond the shock, the wind still moves outward, but it no longer rules what it moves through. It drifts in a wide, warm region between what the Sun governs and what it does not. Both spacecraft are inside that region. Both are still sending. Past the shock, the wind is no longer a wind. It still moves. It simply moves without conviction. The particles that crossed the boundary arrive slower, warmer, and more crowded than they were on the other side. They have given up their speed and taken heat in exchange. This is the region called the heliosheath. It begins where the solar wind slows, and it ends where the Sun's influence finally gives way to whatever the galaxy is made of. Everything between those two surfaces belongs to it. For decades, that region existed only as a number in a model. The models were not careless. They were built by people who understood plasma, magnetism, and pressure balance, and who fed in what the Sun releases and what the galaxy pushes back against it. They solved for the place where those two forces settle their argument. And they returned a thickness, 50 to 70 astronomical units. That was the expected depth of the shell, wide enough that a spacecraft crossing it would need decades. The number felt reasonable. It matched the physics as the physics was then understood. It appeared in textbooks and in diagrams drawn for classrooms, printed as a band of soft color around a small bright center. Nobody had any reason to doubt it. Nobody had a way to check it either. Then a spacecraft went in and measured. Voyager 1 enters the heliosheath in December of 2004. It leaves in August of 2012. 8 years pass between those two dates, all of it continuous motion in one direction. Without turning, without slowing, without pause. And at the end of it, the spacecraft is out. The shell is thinner than anyone had drawn it. Not slightly thinner. The difference is not a small correction to a good estimate, and it cannot be absorbed by adjusting a constant here and a coefficient there. A shell has a thickness for a reason. It is the visible result of a balance. Inside, the Sun pushes outward. Outside, the galaxy pushes back. The shell sits exactly where those two pressures meet and hold each other still. If the shell is narrow, the balance is not what was assumed. There are two ways to make a shell thin. The first is to push harder from outside. If the interstellar medium presses in with more force than the models allowed, the sun's bubble compresses and the wall moves inward. The galaxy would then be a firmer place than the equations described. Denser, perhaps. More magnetized, perhaps, and carrying a pressure that had been quietly underestimated for years. The second way is to push less from inside. If the solar wind loses its energy earlier than expected, it cannot hold as much ground. Something inside the shell would be draining the pressure, taking the wind's momentum and turning it into something that no longer points anywhere at all. Heat, perhaps. Both explanations fit the measurement. Neither can be ruled out from a single crossing. And the data suggests they are not entirely separate. What Voyager finds inside the shell is not a clean, ordered flow. It is a plasma that has lost its sense of direction. Slow, hot, turbulent, the particles no longer travel in one confident line away from the sun, the way they did in the open wind. They wander, they circle, they bunch together, and then thin out again. Some of them appear to sit almost in place, and a few appear to drift backward toward the star that sent them. Stagnant is the word the scientists reach for. It is an unusual word to apply to a wind. A wind that stagnates has stopped being a wind in every sense but its name. A river arriving at a wide, shallow basin does something similar, spreading and slowing, and turning back on itself in slow eddies near the edges. The water is still there. It simply no longer knows which way it was going. The wind arrives fast at the shock and leaves it slow. What it carried as forward speed becomes disorder. Temperature is disorder measured with a thermometer. The plasma there is hot precisely because it stopped moving in a line. And a plasma that mills about does not press outward with the same authority. The wind spends its strength on turbulence instead of on distance. There is another possibility, quieter and stranger. The heliosheath is not empty of visitors. Neutral atoms from the galaxy drift straight through the sun's magnetic defenses. They carry no charge, so the magnetic field does not touch them. They enter the shell without being noticed. Inside, they collide with the slowed solar wind, and charges are exchanged in those collisions. A fast particle becomes neutral and escapes. A slow one becomes charged and stays. Each exchange removes a little energy from the shell. Over a very large volume, a little energy removed many times becomes a great deal. The galaxy, in this reading, is not only pressing on the bubble from outside, it is reaching through it. It is bleeding pressure from within. A wall attacked from both sides thins faster than either side alone would explain. Inside the shell, the material is thin by any earthly standard. A handful of particles in each small volume, spread through a darkness that goes on for years of travel. Almost nothing. And that almost nothing carries structure. The magnetic field carried out from the sun arrives here folded and creased. It has been stretched across an enormous distance, and it no longer lies in neat spirals. It piles up instead, layer against layer, in the slow traffic behind the shock. Nothing out there smooths the creases back out. The folds hold a pressure of their own, and in places that pressure rivals whatever the thinned wind still has left to give. Where the field piles up, it pushes back on the particles caught in it, and the region grows stiffer than the models made it. Through those years, the instruments record a plasma that never quite settles into a pattern. Some months the particle counts rise, some months they fall away. There are stretches where the flow appears to reverse, and quiet intervals that end without warning. The pressure rises and eases on no schedule anyone can name. Each variation has to be recorded and left unexplained for years, because nothing nearby can be compared against it, and no stretch can be sampled twice. The region refuses to behave like a simple layer. It behaves like weather. The spacecraft has no way to stop and look twice. It samples what it passes through, once, at the speed it happens to be traveling. Everything known about that shell comes from a single line drawn through it. One thread. From that thread, an entire structure has to be inferred. That line gives one depth, measured in one direction, on one side of the sun. The shell need not be the same everywhere. Where the sun moves into the galaxy, the wall is pressed harder and should sit closer in. Behind, in the trailing direction, it may reach much farther. A single crossing cannot separate a thin shell from a thin place in the shell. What it can do is rule out the old number. 50 to 70 astronomical units cannot survive an 8-year passage. That much holds no matter which direction the line was drawn in. A second spacecraft is crossing on another path, and its own depth will arrive years later, from a different part of the sky. Until then, there is one measurement, and every model of the outer solar system is being rebuilt around it. The picture drawn for classrooms is redrawn. The soft band around the bright center is narrowed on the page. Out there, the crossing continues in the only way it can. The spacecraft holds its heading. The instruments count what passes. Particles that left the sun long ago drift alongside it in the dark. They keep their heat and nothing else. The edge of the sun's realm was a drawing long before it was a measurement. Not a number, a drawing. It appeared in textbooks long before anything went there. You have almost certainly seen it, a soft blue bubble, rounded at the front, tapering behind into a long trailing tail. The sun sits inside it, small and bright, with the planets gathered in a tight cluster near the center. Arrows come in from the left to show the wind of the galaxy. The bubble leans away from those arrows, like a flame leaning away from a breeze. It is beautiful. It is also, as far as anyone can now tell, wrong. The shape came from analogy, which is how most pictures of unseen things begin. And analogy is persuasive long before it is ever tested. A comet has a head and a long tail streaming away from the sun. The Earth's own magnetic field has a rounded front and a drawn-out wake behind it. Something moves through a fluid, and the fluid piles up in front and closes slowly behind. So the sun moves through the thin gas between the stars at its own steady speed, and it ought to leave the same signature in that gas. A blunt nose and a long quiet tail stretched out behind it. Every drawing agreed with every other drawing, which felt like confirmation and was only repetition. No one had been there. The picture was a guess wearing the confidence of a diagram. Then the two spacecraft crossed the boundary, years apart, and the drawing began to come undone. The trouble was not that either crossing was strange in itself. The trouble was that they did not belong to the same picture. The two probes did not leave along the same line. The planets they visited had thrown them onto very different paths decades earlier, and nothing after that could change where they were going. One went out above the plane where the planets orbit. The other went out below it. By the time they reached the boundary, they were sampling it at latitudes far apart, different corners of the sky, different parts of an unseen surface. Neither probe was built to measure a shape. Each was built to fly past worlds, and the boundary came later, as a leftover of paths chosen for entirely other reasons. At first, this looked like a gift. Two probes touching the same wall in two places is better than one. It sounded like the beginning of a map. Instead, it became the beginning of a problem. The first crossing had looked like a fact about the boundary itself. The second showed that it was only a fact about one place. If the boundary were the smooth, comet-shaped bubble of the diagrams, the two crossing points would fall in predictable places on it. They did not. The wall was not where the shape said it should be. Not for both of them at once. You could adjust the model to fit one crossing perfectly. Stretch it, or shorten it, or tilt it, and one probe would land on the surface you had drawn, while the other sat somewhere the surface was not. Push the model back the other way, and the two errors simply changed places. The second probe landed on the surface. The first fell off it. Not a dramatic contradiction, just a shape that has to be bent to hold both places at once. The bending is the tell. The long comet tail was the first casualty. If the bubble trailed away behind the sun in a narrow stream, its sides would flare in a particular way, and the crossings would sit on those sides. They did not. So the tail, if it exists at all, is not the tail that was drawn. It was never measured, only extended. Other shapes were offered in its place. Some modelers rounded the bubble off and gave it almost no tail at all. Others split it into two lobes, like a crescent held open by the magnetic field of the galaxy. A few let it slacken into something softer, less like a bullet and more like a balloon losing its air. Each of these can be made to fit one crossing. None fits both without strain. There is also the matter of when the crossings happened. They did not happen together. Years separate them. Nothing guarantees the wall stood in the same place for both. Each probe reported where it stood at one spot, on one day, and neither recorded where that wall had been the year before or after. Two crossings, two moments. And here is the part that is easy to say and hard to sit with. 2 points do not determine a surface. This is not a limitation of the instruments. It is geometry, and geometry does not negotiate. An infinite number of surfaces can be drawn through any 2 points in space, and no amount of care in the measuring reduces that number by even one. Smooth ones and wrinkled ones, wide ones and narrow ones, ones with a tail, ones without. Every one of them passes through both points exactly, and every one of them describes a different solar system. Sailors once sounded the ocean floor with a weighted line, reading the depth at the moment it stopped. 2 soundings, taken far apart, give 2 depths. They say nothing about whether a trench lies between them, or a ridge, or a long, flat plain. You can join the 2 depths with a line and call it a seafloor. It will look smooth and reasonable, and be almost entirely invented. The line was drawn anyway. None of this makes the question hopeless. It makes it underdetermined. That is a gentler condition, and a more permanent one. You can add assumptions to close the gap. Assume the shape is symmetric about some axis, and 2 crossings become enough to fix it. The assumption supplies everything the measurements do not, so the model ends up looking constrained by a hand rather than by anything a probe ever found out there. But the symmetry is the thing you are trying to measure, assuming it is not learning it. This is why the honest version of the current picture is a strange sentence. We know the shape in the textbooks is wrong. We do not know what the right shape is. Those 2 statements are usually not allowed to stand together. Normally, showing that an answer is false comes with some hint of the better answer waiting behind it. The falsification arrived alone. The old drawing has been removed, and nothing agreed upon has been put in its place. There are candidates, and each candidate has people who can defend it with real arguments, drawn from the same small pile of measurements everyone else is working from. None of them can defeat the others. Astronomers have a quiet phrase for this situation. The model is not constrained. The phrase marks a hole where an answer will eventually go. The gap closes only by adding points. A third crossing, far from the other 2, would rule out a great many surfaces. A fourth would rule out more. Nothing is in position to provide either one. The only machines beyond the wall are the two that already went through, and neither can come back and cross somewhere else. Every new point would have to be launched and then waited for. The waiting is measured in careers, not in seasons. Meanwhile, the two probes continue outward along their separate paths. They climb farther above and below the plane of the planets with every year that passes. And the distance between them grows in a direction no map covers. Each is now moving through a region no instrument has ever occupied. There is no third probe behind them to check what they found, and no plan on any desk that would put one there. Behind them, the shape they crossed is still being argued over. A magnetic field has a strength and a direction. The strength tells you how tightly it holds. The direction tells you where it came from. For decades, Voyager 1 measured a field made by the sun. Its magnetometer sat far out on a long boom, away from the spacecraft's own small currents. It read the field steadily, day after day. 3 axes, 3 numbers, over and over. From those numbers you can build an arrow. The arrow has a length and a heading. Out at the edge, that field is very weak. It is far weaker than the field at the surface of the Earth. But it is steady. It has a shape, and the shape belongs to the sun. The sun turns. Its magnetic field is anchored in that turning surface. The wind carries the field outward. The result is a spiral. Water leaving a spinning sprinkler makes the same shape. Each drop travels straight outward, but the line of drops curves. Close to the sun, the lines still run almost straight out. Far away, they have been wound many times around. By the time the solar field reaches Voyager, the spiral is very tight. The field lines lie nearly at right angles to the direction of the sun. That was the field Voyager had been reading for decades. Beyond the heliopause, the field is not the sun's. It belongs to the galaxy. Every spiral arm carries one. It threads the gas between the stars, folded and stretched by every explosion that ever happened nearby. It has no memory of our sun at all. It was there before the sun formed. It answers to other things, older and much larger. So the crossing should have been obvious. Not just a change in strength, but a change in aim. Every model said so. The field on the far side should point somewhere else entirely. Some models allowed a modest turn. Others expected the direction to swing right around. Nobody wrote down a number close to 0. On August 25, 2012, Voyager 1 crosses at 121.7 astronomical units. The strength of the field jumps. It rises by about 60%. That part was expected, and it makes sense. Interstellar gas presses in on the heliosphere from outside. The field caught in that gas is compressed against the boundary, like snow packed against a fence. Compressed field is stronger field. So the jump in strength was almost a relief. It looked like the textbook. Everything matched the drawings on the wall. Then the team looked at the direction. The angle changed by less than 2 degrees. 2 degrees is very little. A thumbnail held out at arm's length would very nearly cover it. The field on the far side of the solar system pointed almost exactly where the sun's field had been pointing. The first response was to doubt the instrument. That is always the first response. The magnetometer was checked against its own calibration rolls. The spacecraft turned itself slowly, on purpose, so the sensors could look at the field from every angle. Those rolls had been done for years. They were done again. The instrument was fine. The number held. Whatever had happened out there, the spacecraft had reported it correctly. There is a reason this mattered more than the strength. Strength can be faked by many things. A shockwave passing through raises it. A gust of solar wind raises it. Compression at a boundary raises it. Direction is harder to fake. Direction says whose field you are inside. And the direction was saying that the field outside was lined up with the field inside. Two magnetic fields with no shared history, no shared source, and no reason to agree. Pointing the same way. Nobody had a mechanism ready for that. The simplest explanation is that the local interstellar field is combed. Not everywhere. Only here. The heliosphere is a bubble sitting in a slow interstellar flow. The bubble pushes outward, and the flow pushes back. Magnetic field lines caught in that flow cannot pass through the bubble. They wrap around it instead. They drape over the heliosphere the way a cloth drapes over a stone. A river moving past a stone does something similar. The flow lines bend to follow the surface. They hold that bend for a while before they straighten out again. If the draping is strong enough, the field just outside would be pulled into line with the boundary itself. And the boundary is shaped by the sun. So the outside field would be wearing the sun's shape without belonging to the sun. It would also mean Voyager did not measure the true galactic field at all. It measured a local layer that our own star has bent out of true. The undisturbed field would begin somewhere farther out, past the draped region, at a distance nobody can name. The second explanation is different, and in some ways stranger. Perhaps the heliopause is not a surface. We draw it as a line, because a line is easy to draw. But a real boundary between two magnetized gases does not stay clean. It ripples. It folds. Bubbles of one side get pinched off and swallowed by the other. Magnetic field lines from inside connect with lines from outside and rearrange themselves. That process has a name in plasma physics, and it is seen all the time near the Earth. If the heliopause behaves that way, then it is a region, not an edge. It could be a thick zone where the two fields mix together and slowly trade places. A spacecraft crossing into that zone would find solar field and interstellar field interwoven. The direction it measured would be an average of both. An average dominated by the field it had been sitting in for decades. The change would come later, gradually, as the mixture shifted. The edge would be a slow trade rather than a step. Under this picture, Voyager did not cross a wall in 2012. It entered a border country. Voyager 2 was the natural test. It crossed later, at a different place, on a different part of the bubble. The two spacecraft had been flying in different directions for a long time. Voyager 2 carried a magnetometer that was still working well. If the alignment were a local accident, the second crossing should have looked different. It did not. Voyager 2 found the same thing. The field grew stronger and kept its heading. Two spacecraft, far apart on the boundary, reported the same quiet refusal. That made the result harder to dismiss and harder to explain. One measurement can be a fluke of geometry. Two measurements at two different points on a curved boundary are a property of the boundary. Models were rewritten. Draping was strengthened in the simulations. The boundary was made thicker. Some groups added turbulence, small eddies in the interstellar gas that would blur any sharp change in direction. Some tilted the whole heliosphere in the models. Then Voyager's path would graze the boundary instead of punching through it. Each adjustment brought the models a little closer. None of them landed on 2 degrees without being told to. That is the part that still sits unfinished. A model that has to be tuned to match an answer is not a model that predicted it. In 2026, the question is still open. The papers are still being written. The 2 Voyagers are still out there, still sending numbers back, growing fainter every year. Their magnetometers are among the last instruments left running. The field they report has changed slowly since the crossing. It has drifted, a few degrees here, a few there, the way a compass needle settles. But it has never made the sharp turn the models drew. Somewhere out ahead, the field must eventually forget the sun. There must be a place where the lines run as the galaxy laid them. A place indifferent to the small bright star that made this bubble. Nothing in the data says where that place begins. Voyager may reach it. It may already have passed through it without noticing. The instruments do not carry a marker for it. They only send back a strength and a heading. And for now, the heading is still the one the sun gave it. There is an instrument on Voyager 1 that stopped working in 1980. It was called the Plasma Science Experiment. It counted particles. It caught them, sorted them by energy, and reported how many there were. That is the most direct way to measure a density. You put a cup in the wind, and you see what falls in. In 1980, the cup broke. Something in the electronics failed quietly, past Saturn, and the engineers found nothing they could repair from the far end of a radio signal. The instrument stayed aboard for years without returning anything worth reading, and it was switched off long after the failure. By then, there was no reason left to feed it power. Nobody in 1980 was planning a measurement for 2012. The mission that had been funded ended at Saturn. Everything after that was a gift. And gifts are not planned for. The detector went dark 2 years before the moment it would have been built for. The one instrument that could have answered the question directly was already long dead when the boundary arrived. Density is what separates the two regions. It is the cleanest line between them. Inside, the solar wind is thin almost past belief, and outside the interstellar gas is thicker by a factor large enough to see plainly. Both numbers are emptier than the best vacuum ever made in a laboratory. But the ratio between them is enormous. A ratio is something you can measure. So the crossing has a signature, and the signature is a number. Two numbers, really. One on each side. There was another instrument still alive. It was not designed for this. It was called the plasma wave subsystem. Its antennas were built for other work. It picks up electric fields. Not particles, not counts, just the trembling of charge in the space nearby. It turns those fields into a signal. The signal has a frequency, and for most of the mission reading it was a background task. It listened to waves rolling through the solar wind, useful work of the quiet kind. Then it became the only way to weigh the space around the spacecraft. The trick rests on something plasma does on its own. A plasma is gas that has come apart. It is not a crowd of whole neutral atoms anymore. The electrons have been separated from the nuclei. Both drift free. And because the charges are free, they can be pushed. And because opposite charges pull on each other, a push does not just move them. It makes them come back. Displace the electrons a little, and the ions tug them home. They overshoot. They swing past, get pulled back again, and swing the other way. The plasma rings at a single pitch, like a struck bell or a plucked string. The frequency of that ringing depends on almost nothing. Not on temperature. Not on the strength of the magnetic field. Not on which direction the plasma is moving. It depends on how many electrons there are in a given volume. More electrons, faster ringing. Fewer electrons, slower ringing. The relationship is clean, and it is one of the first things a plasma physicist learns. So if you can hear the pitch, you can count the electrons, and you do not need to catch a single one of them. You only need to hear the medium move. The problem with a bell is that it has to be struck. Space does not ring on its own, not loudly, not in a way an antenna can resolve. Something has to hit it. The sun provides the hammer, though it takes its time about it. A large eruption leaves the sun as a wave of pressure and field. It travels outward for months, spreading and weakening and mixing with the wind already in flight. By the time it arrives, it is barely a shock. Just a slow rise in pressure, a broad shoulder rolling through the gas. The wave squeezes the medium, and the medium answers the only way it knows. For days, sometimes weeks, the plasma around Voyager 1 oscillates, and the antennas hear it. The signal is faint, but it sits at a definite frequency, and a definite frequency is a number you can convert. The conversion is short. One line of arithmetic, done on the ground. Frequency in, density out. This is how the measurement was actually made. Not by a detector counting particles, but by a listening post catching an echo. An instrument doing a job that nobody had assigned it. The numbers came back small. In the thinned-out solar wind near the boundary, the answer was about 0.02 of a particle per cubic centimeter. Write that as 0.002. Draw a cube 1 centimeter on a side out there, and most of the time it is empty. You would need 500 such cubes to find one particle on average. That is the wind of a star at the end of its reach, thinned by every mile it has crossed. Then the same instrument, listening to a later event, reported something different. Around 1/10 of a particle per cubic centimeter. Write that as 0.1. 50 times more. The instrument had not changed. The arithmetic had not changed either. A factor of 50 is not a drift. It is not the sort of wobble a medium makes while staying where it is. The interstellar gas is denser because nothing is blowing it outward. The sun pushes its own gas away, and the further that gas travels, the more room it has and the emptier it gets. The galaxy's gas just sits there at the density the galaxy gives it. So the boundary between the two shows up as a step in the numbers. Voyager 1 measured that step with a broken toolkit and a borrowed method. That makes it an indirect measurement, and physicists are careful with the word indirect. It means the quantity was inferred through a chain of physics rather than read off a dial, and the chain here is short. Still, it took time to be believed. One event is not a measurement. The first oscillation events were sparse. They came only when the sun happened to have sent something outward months before. And you cannot schedule a solar eruption. The team had to wait for the star to speak, then wait again for the sound to cross the distance and arrive. Between events there was nothing to do but hold on to the old number and hope the sun would supply a new one. Confirmation arrived the way it usually does in this line of work. Slowly, in pieces. From the same instrument saying the same thing twice. The events themselves are read as pictures, not as tables of numbers. Frequency runs up one axis, time runs along the other, and an oscillation shows up as a bright line across the dark. It holds its pitch for days and then fades out of the record. Sometimes the line does not hold. It climbs slowly while the wave is still passing. A drift like that carries information of its own. A rising pitch means the electron count is going up. A falling pitch means the gas out there is thinning. So the instrument does not deliver one number and stop. It delivers a sequence. One reading for every time the sun shouts loudly enough to be heard. The electrons doing the ringing are the same electrons being counted. Nothing foreign is sent into the medium to probe it. Nothing is brought back either. The gas is asked to describe itself, and the description comes back as a pitch. Meanwhile, the spacecraft keeps moving. It has no way to hold still. It cannot stop, and it cannot go back to take a reading twice. Each number belongs to a piece of space that is already behind it. Voyager 2 takes the other road out. It leaves on a southern arc, angled below the plane of the planets. It travels a little slower. For years it follows its twin toward the same invisible wall, always behind, moving through a part of the sky the first probe never saw. On November 5, 2018, it reaches that wall. The distance is 119 astronomical units. 119 times the space between the sun and the Earth. The solar wind falls away. The particles from outside rise to meet it. The heliopause closes behind the spacecraft, and Voyager 2 is in the interstellar medium. This is the second crossing in history. But it is the first one that anybody actually watches. The difference comes down to a single instrument. Voyager 2 still carries a working plasma detector. Its twin does not. That detector had failed long before the boundary, decades earlier, quietly, so the first crossing had to be read sideways. Everything about the plasma out there had to be inferred from other instruments. Inferred from counts of cosmic rays. Inferred from the bend of a magnetic field. Good science, careful science, but always one step removed from the thing itself. Voyager 2 does not have to infer. It can taste. That is a rare kind of luck in this work. An instrument older than most of the people now reading its numbers, still awake, still arriving exactly where it is needed. Nobody who designed those cups expected them to be used here. The instrument is a simple idea carried very far from home. It is a set of cups facing outward, open to space. Charged particles drift in. Each one carries a tiny current with it. The instrument counts those currents at different energies. From the pattern of counts, it builds a picture of how fast the particles are moving. Not a single speed, a spread of speeds. Some particles slow, some fast, most somewhere in the middle. That spread is the whole measurement. Because temperature, in a gas, is nothing more than that spread. Temperature is not a feeling. It is a number describing how violently the particles jostle. A cold gas has particles that move slowly and agree with each other, while a hot gas has particles that move fast and scatter widely. So when the cups fill with interstellar particles, they are reading a temperature directly. The cups do not model anything. They simply add up what falls into them. The number that comes back is around 40,000 Kelvin, roughly twice what the models had predicted. 40,000 Kelvin is a strange number to sit with. It is hotter than the surface of the sun. It is far hotter than any flame you have ever stood near. The surface of a star, out in the dark between stars. And yet the spacecraft flying through it is not harmed at all. Nothing melts, nothing glows. No instrument reports a rise in heat. Voyager 2 keeps running cold, exactly as it did the day before. Temperature and heat are not the same thing. Temperature tells you how fast individual particles move. Heat tells you how much energy actually gets transferred. To transfer energy, particles have to arrive. They have to hit something, again and again, and give up a little of what they carry each time they do. And in the interstellar medium, almost nothing arrives. The gas out there is thinner than any vacuum ever made on Earth. Thinner than the best laboratory chambers, by a wide margin. So each atom is moving with real violence, and there are so few of them that the violence never gathers into anything. A single atom crosses the detector, and then there is quiet. The total energy in a cubic meter of that gas is close to nothing. Spread that nothing across the metal skin of a spacecraft, and it disappears. The comparison people reach for is an oven. The air inside a hot oven and the metal rack sitting in the middle of it hold exactly the same temperature, degree for degree. You can hold your hand in the air for a moment without harm. Touch the rack, and you are burned instantly. Same temperature. Very different amount of matter waiting to give you its energy. The interstellar medium takes that idea to its limit. It is the thinnest oven imaginable, and its walls are almost entirely missing. In fact, the spacecraft loses more heat than it gains out there. It radiates energy away into the cold constantly. The heat it produces leaves faster than the gas outside can replace it. Its own decaying plutonium is the only real source of warmth it has. The 40,000 Kelvin gas around it is, in practical terms, an empty room. So the temperature is not a danger. It is a message. A gas holds its heat only if something keeps putting energy in. Left alone, a hot gas cools. It radiates, it expands, it settles. 40,000 Kelvin sustained across a region this large means the local medium is being stirred by something that has not stopped. Something is depositing energy into it faster than it can shed that energy. The candidates are the ordinary violence of the galaxy. Ultraviolet light from hot young stars, arriving from very far away, stripping electrons off atoms and leaving them moving faster than before. Shockwaves left over from stars that exploded long ago and are still spreading outward through the thin gas that lies between them. Turbulence in the magnetic field, folding and snapping and dumping heat into the particles. Each of those was known. What the measurement changed was the accounting. The old models had assumed a quieter neighborhood. They pictured the gas just outside our bubble as calmer, older, more settled. They had good reasons for it. Before Voyager 2, nearly everything known about that gas came from starlight. Light from distant stars crosses the local medium on its way to us. The gas absorbs a little of it at very specific wavelengths. From the shape of those absorption lines, you can estimate temperature. But that estimate averages over enormous distances. It smears together cold pockets and hot pockets and gives you one number. The models were built on those averages, and averages hide their extremes. A very hot, very thin pocket barely moves the average at all. It can sit right on our doorstep and leave almost no trace in the starlight that passes through it on the way here. There was also a simpler bias at work. The heliopause was imagined as a clean edge. Solar wind on one side, interstellar gas on the other, quietly meeting. The real boundary is not clean. It is a region where the two mix, compress, and heat each other. The two plasmas push against each other and neither wins cleanly. Voyager 2 crosses through that region, not around it. Part of what it measures is gas that the sun itself has already pushed on, compressed, and heated before the spacecraft ever got there. So the number is honest and complicated at once. 40,000 Kelvin is what the instrument finds. Some of that heat belongs to the galaxy. Some of it belongs to the collision our star is having with the galaxy. Separating the two is still being worked on. That is the ordinary shape of a discovery. A prediction is made from good but indirect evidence. A machine finally arrives and reads the thing itself. The number comes back wrong. And the wrongness is the useful part. Every earlier number about the local interstellar medium was a guess refined by distance. This one is a reading taken in place by a set of small metal cups at a temperature nobody expected. The cups keep reporting. Every reading since the crossing has come from inside the same hot, thin gas. The numbers arrive slowly, a few bits at a time, and each one is a measurement nobody could have made from here. Everyone expects silence. That is the reasonable guess. Beyond the reach of the sun, the material between the stars is almost nothing at all. A scattering of particles, spread across distances that have no useful comparison. That is not what the spacecraft finds. The instrument listening out there is not a microphone. It does not sense sound. Sound needs air, and there is no air anywhere along this path. What it senses is electric fields. Small ripples in the charged gas the spacecraft is drifting through. The antennas that pick them up are thin booms, stretched out from the body of the spacecraft and left there since launch. They have no moving parts and nothing to wear out. Plasma does something ordinary matter does not. Disturb it, and the free electrons swing back and forth around the heavier ions they left behind. They overshoot, pull back, overshoot again. The whole cloud rings at a frequency set by how crowded it is. Denser plasma rings higher. Thinner plasma rings lower. That relationship is clean. It does not care about distance or darkness. If you can measure the frequency, you can count the particles. That is the whole method, and it is why a machine sitting in the dark can still report on the material around it. For years, that measurement arrives only in bursts. The sun produces a large outburst. The shock front travels outward for months. When it finally reaches the spacecraft, it strikes the surrounding plasma the way a hand strikes a drumhead. The gas rings. The antennas register the tone, and the density can be calculated. Then the ringing fades and the data go quiet again. It works, but it is rationed. One measurement, then a long wait for the sun to be generous a second time. Sometimes a very long stretch passes between readings. The picture of the interstellar medium arrives as scattered dots, far apart, one for each time the sun happens to shout loudly enough to be heard. Everything between them is assumed rather than known. Then, in 2017, the record changes. The plasma wave instrument reports something faint. It is very weak, near the floor of what the antennas can detect. It is narrow, occupying a thin slice of frequency rather than a broad smear. And it does not stop. There is no solar outburst before it, no shock front arriving, no sudden strike, no decay afterward. The signal is simply there, holding steady, week after week. It survives the checks that usually kill a weak detection, turning up again in later data and in records already stored from earlier months. The engineers look for a fault first, as they always do. An electrical hum from the spacecraft itself would be the obvious answer. Old hardware makes noise. Heaters cycle, motors twitch, and power systems leak faint tones into every antenna aboard, the ordinary background of a machine that has been running for decades. But those signals have signatures, and the team has studied them for decades. This one matches none of them. It holds its frequency no matter what the spacecraft is doing. The tone belongs to the gas outside. The conclusion is strange and simple. The medium between the stars is vibrating on its own, everywhere the spacecraft goes. No shock sets it going, and no push from the sun keeps it there. A hum. The word is imprecise, and the scientists know it. Nothing is making a sound out there. If you were standing in that plasma, your ears would report nothing at all. But the oscillation falls in a range that can be shifted into audio without much manipulation, which is the only reason any of it can be played back. When that is done, the result is a thin, steady tone. It wavers slightly. It rises and falls in small amounts, like something breathing very slowly. And it holds. The interstellar medium has a voice, and the voice is a single sustained note. What matters more than the sound is what the sound makes possible. Before this, density is a series of snapshots. After this, density becomes a line. The hum is always there, so the frequency can always be read without waiting for the sun. Read the frequency, and you have the electron density at that exact position, at that exact moment. The spacecraft never stops moving. Each new reading comes from plasma no instrument has ever occupied. A sample taken once and never available again to anyone. The line grows by itself, 1 point at a time, at whatever speed the spacecraft happens to be traveling. Stretch that record out, and a shape appears. Across roughly 30 astronomical units of interstellar space, the density is not constant. It climbs. Not sharply, not in steps, but gradually, across a stretch of space that takes years to cross. The spacecraft moves deeper, and the medium slowly thickens around it. This is not what a smooth, uniform void would do. It suggests structure on a scale nobody could resolve from inside the solar system. Something large is arranged out there, and the spacecraft is passing through the edge of it. That is a long baseline for a single instrument, and no telescope on Earth can sample the density of the medium along a line like that. Layered inside that slow climb is something smaller. The hum is not perfectly flat. Its frequency jitters in small amounts on shorter timescales. The density itself is fluctuating as the spacecraft moves through it. Pockets slightly denser and pockets slightly thinner sit packed inside the larger trend. Too small and too quick to appear in any single reading. Turbulence, the same word used for water in a river and air over a wing. Here it applies to gas so thin it barely qualifies as a substance. The interstellar medium is stirred. It is not a still room. It is something moving slowly, on scales that dwarf anything a person can hold in mind. That fact can only be learnt this way, by a machine that listens without stopping while it is carried through the gas it is measuring. An occasional snapshot, years apart, would never have shown it. The fluctuations happen faster than the rationed measurements can catch them. Continuous listening is the only method that reaches them. Nothing about the gas changes in 2017. Only the way it is being watched. The hum is not dramatic. It is not a signal from anyone. It carries no message and no intent. It is the sound of matter being matter, in a place where there is almost none. The electrons out there are pushed and pulled by whatever passes through. They answer at the only frequency they know. The tone holds at the level the local density sets for it, waiting for nothing and answering to nothing. The spacecraft that hears it was not designed for the job. Its instrument was built to study the plasma around the outer planets. It was never expected to still be running this far out, decades after the last of the work it was built for was finished. It simply keeps listening after there is nothing left in the plan to listen to. The gas it happens to be sitting in becomes the most informative thing still within reach of its antennas. And the listening turns out to be the point. The note moves with the spacecraft, shifting by fractions as the surrounding density changes. Every shift is a fact about a region nothing built by anyone has ever occupied. The record is still open at one end. The climb has been traced across the distance already covered. Nothing in the numbers says where it levels off. Whether the density keeps rising, flattens out, or turns back down is a question only the next stretch of gas can answer. The turbulence sits inside the same limit. Its finest ripples are smaller than the record can resolve. Its largest may be wider than the whole path measured so far. Both ends of that scale are still outside the data. The interstellar medium is not still. It moves. Waves travel through it, the way weather travels through an atmosphere, and they arrive at the spacecraft in a particular order. They are not made of air. They are made of plasma, of charged particles, and the magnetic field threaded through them. The shock comes last. Ahead of each shock, a beam of electrons runs forward along the magnetic field lines. They travel faster than the disturbance that launched them. They are the lightest particles the field carries. The field lines act like rails. The electrons slide along them and arrive early, well before the disturbance itself. And when they get there, they set the plasma around the spacecraft ringing. The beam is thin and quick. It carries no shock with it, only the news that one exists. The local electrons begin to oscillate. They move back and forth at a rate the plasma itself decides. That rate depends on the plasma, not on whatever set it going. The instrument hears the oscillation first, not the shock. The wave that runs in front of it. It is a kind of warning, a sign that something larger is on its way. Sometimes the shock follows, sometimes it does not. or it passes too far away to register. But the order never reverses. The beam and the oscillation and the shock are three parts of one event, pulled apart in time by the speed each of them travels. The spacecraft has no forward view of the plasma it is about to enter. It only knows what touches it. So the region is mapped one crossing at a time. One shock, one oscillation, one change in the field. Each crossing is recorded in full, and then it is over, and the instruments go back to waiting. Each event is a single point in a volume far too large to survey. The points are separated by long stretches in which the field barely changes. The magnetometer keeps reading through those stretches anyway. It takes its samples on a fixed cadence and sends them home whether anything is happening or not. Most of what comes back is the sound of nothing arriving. Then a reading changes. For years, the events came and went in a shape the instruments learned to recognize. The magnetic field would rise as a disturbance passed. It would hold for a while, then fall back towards something close to its earlier value. A wave came through, and the medium settled behind it. The baseline always returned. Between 2021 and 2022, that pattern breaks. Voyager 1 enters a long increase in the magnetic field. It is not sudden. The instrument records the strength rising, and continuing to rise, and the increase never resolves into an event with two ends. Researchers give the feature a name: the magnetic hump, a plain name for something that did not behave. Every earlier event had two sides, an increase and a matching decrease. The hump has only one. The magnetometer had logged many disturbances before it, and every one of them had closed, which is what made this one stand out in the record. Nothing in the readings before it marked the plasma ahead as different from the plasma already behind. The field goes up, the baseline moves with it, and years later, it has still not come back down. The spacecraft has crossed into a region that is simply different from the one behind it. The instruments were never built to say why. They record that the field went up and remained there. That is the whole of what one spacecraft can offer. It says nothing about how far that place extends. For that, you would need a second measurement, somewhere else. And there is a second measurement. Voyager 2 is out there too, in a different direction entirely. They are not following each other. One leaves the plane of the planets one way, the other leaves it the other way. They sample two separate points on an enormous surface, and they move a little further apart with every year that passes. Both carry magnetometers of the same design. Both read the strength and direction of the field around them. Both have been sending those numbers home for decades. For a long time, that was assumed to be redundancy. Two probes, two confirmations, one interstellar medium. The two crossings happened years apart, in directions that point away from each other, and nobody expected that to matter much. The comparison was supposed to be simple, one record laid against the other. It did not work out that way. Voyager 1 recorded fluctuations in the magnetic field that were strongly marked. The variations were sharp, the swings were large, and they held up across the whole length of that record. They were among the most distinctive things its magnetometer had ever registered. Voyager 2 did not find them. The same kind of instrument, the same measurement, and nothing of that sort in the record at its location. Two spacecraft in the interstellar medium do not report the same interstellar medium. The boundary is not the same everywhere you cross it. For most of the mission, the mental picture had been simpler. A bubble with an edge, and beyond the edge, a different medium. Cross the edge, and you are outside. Every crossing the same crossing. The two records do not fit inside that picture. The edge has texture. What replaces the bubble is a wide zone with no clean rim to it. changing character from one place to another. There are regions where the field ripples violently, and regions where it lies almost still. A surface that large holds quiet stretches and violent ones at once. The way an ocean holds calm water and heavy water on one afternoon. The structure runs on scales large enough to put two probes into genuinely different conditions. Neither of them is wrong. They are both measuring correctly, in places that do not resemble each other. This changes what a single measurement means. Before, a reading from Voyager 1 could stand for the interstellar medium in general. Now it stands for one path through it. The magnetic hump belongs to that path. Whether it exists elsewhere along the boundary, nobody can say. Voyager 2 was not in a position to check. It was crossing somewhere else, seeing something else. 2 spacecraft is the largest sample anyone has ever had out here. 2 points cannot define a surface. They can only show that the surface is not simple. The shocks still pass, and the electron beams still run ahead of them along the field lines. The oscillations still arrive first, and the instruments still record them. The mechanism is the same in both places. The field it travels through is not. Somewhere in the volume between the 2 paths there has to be a transition. Somewhere the strong fluctuations give way to the calmer field. Nothing in the 2 records says whether that transition is narrow or vast. Nothing marks where it begins. The 2 Voyagers are the only instruments that will report from that side of the boundary in this lifetime. The inference is not finished. It may not be finishable with the data anyone will have. The width of the boundary stays a matter of reasoning, drawn from 2 thin records and whatever can be argued from them. What the 2 of them are drawing is not a map. It is 2 lines. Each new reading adds a little length to a line. The lines run outward from the same origin and open away from each other. The magnetometers keep the cadence they have kept since launch. Whatever passes through the boundary next will be met by one of them, or by the other, and never by both at once. The 2 records will be compared again, and the gap between them will be a little wider than it was. The spacecraft continue outward through whatever region they are in. The distance between them grows a little with every day. There is a number that governs everything the 2 spacecraft are still allowed to do. It is measured in watts. Each probe carries generators that turn heat into electricity. The heat comes from plutonium, decaying quietly inside a metal shell. Decay does not pause. It does not slow down for a good year or speed up for a bad one. It follows a curve that was known before either spacecraft left the ground, and the curve has never once been wrong about what came next. Roughly 4 watts disappear every year. 4 watts is almost nothing on Earth. It is less than a small bulb in a hallway. It is the difference between a warm hand and a cool one. But out there, 4 watts a year is the entire shape of the future. The generators do not fail suddenly. They simply give a little less each time anyone asks. And the flight team has to decide, in advance, what that little less will cost. This is the part of the mission that nobody imagined when it began. The instruments were built to be switched on. Nobody wrote a careful procedure for switching them off. That procedure had to be invented decades later, by people who inherited the spacecraft from strangers and learned its habits from paper. They call it managing the power budget. It is a gentle phrase for a difficult thing. What it means is that every watt spent on one instrument is a watt some other instrument will not have next year. Every year, a small group sits down with a list. On the list are the instruments still drawing current. Beside each one is a number, in watts, and a sentence about what it measures. The group has to choose which sentence stops being written. If nothing is turned off, the voltage sags, and something else fails on its own. Something unplanned. Something that might take the whole spacecraft with it. So the choice is not between losing an instrument and keeping it. The choice is between losing one on purpose and losing everything by accident. They think in orders, not in single decisions. Which instrument goes first, and which one after that, and which one is protected until the very end? They weigh what each instrument has already given against what it might still find. They weigh redundancy, because some measurements exist in two forms. They weigh the fact that one probe can sometimes cover for the other, since the two are far apart and moving through different directions of the same dark. And they weigh a fact that hangs over the whole table. Nothing they turn off will ever be turned on again. There is not enough power to bring a sleeping instrument back. An instrument that stops is an instrument that has finished. Its last measurement is already in the archive, taken on an ordinary day, before anyone in the room knew it was the last one. In February of 2025, the cosmic ray subsystem receives its final command. The instrument has been listening for decades. It has counted particles arriving from far outside the solar system. There is no ceremony on board. A relay moves, a current drops, and the counting stops. On the ground, a line on a display goes flat and stays flat. Some of the people watching had worked with that data since they were young. They had learned to read it the way you learn to read handwriting. Now the handwriting ends mid-page. The saved power is small. It buys months, not decades. But months are what the mission trades in now. Then comes the 17th of April, 2026. The low-energy charged particles instrument is switched off. It had been measuring the slower particles, the ones that drift rather than race. Its share of the budget goes back into the common pool, where it will be spent keeping what remains of the payload warm enough to work. After that April, the count is easy to say and hard to hear. 2 science instruments remain active on Voyager 1. 3 remain active on Voyager 2. 5 sentences. That is what is left of a payload that once filled a table. Each surviving instrument is now doing work that no longer has a backup. If one of them falters, there is nothing beside it to take the reading. The people who manage this speak carefully about it. They do not say the mission is ending. They say they are extending it. And that is true, because every watt saved is another stretch of listening. But they also know what the curve does. The curve does not care how carefully anyone budgets. It only cares about time, and the whole exercise is about how slowly that time can be spent. So alongside the shutdowns, there is another kind of work. Quieter work, done in simulations and old manuals. The question is not only what to turn off, but what to run differently. A spacecraft is not one machine. It is a collection of components, some of which have twins. Some of those twins draw less current than the ones in use. Some were never meant to be primary at all, and were carried only as spares that nobody on the original team expected anyone to need. In the months before the test, engineers build a plan around exactly that. They call it the Big Bang. The name is a joke among people who work with very old hardware. It refers to how much changes at once. Instead of one careful adjustment, the plan moves several components together in a single sequence. Heaters, switches, paths through the electronics. Each one is asked to do its job through a linear route. Each change is small. Added up, they matter. The goal is to keep the voltage above the line where the spacecraft starts protecting itself. Below that line, things shut down in an order chosen by a machine rather than by anyone on Earth. Every one of these moves is rehearsed on the ground first, on hardware that never flew, in rooms built to imitate a spacecraft nobody can reach. There are engineering models, decades old, kept precisely for this. They reproduce the wiring and the logic. They reproduce nothing else. A model on a bench has not spent a working lifetime in the cold. Its parts have not been drifting slowly out of tolerance the whole time. So a rehearsal tells the team what should happen, not what will. The distance between those two words is the reason the work goes slowly. Every command is written out, read back, and checked by someone who did not write it. Then it waits, sometimes for weeks, while the sequence around it is verified. In May of 2026, the plan is tested for the first time on Voyager 2. Not on paper. On the spacecraft itself, far out in the dark. The commands go up in stages. Nothing is attempted all at once. Because a plan named for a single loud event is carried out with as much patience as the schedule allows. The testing continues through June. Each step is checked before the next one is allowed. Voltages are compared against predictions, line by line. Temperatures are watched, because heat is power too, and a spacecraft that gets too cold stops working just as surely as one that runs out of current. By the end of June, the picture is clear enough to state. The changes hold. The spacecraft accepts them. The gain is measured in about a year. Nothing new was built. Nothing was repaired. Something was only rearranged very carefully inside a machine that no hand will ever touch again. The instruments that are left keep drawing their current. They will keep doing that until the arithmetic comes around again and one more name has to be crossed off the list. The generators keep giving 4 watts less each year, on schedule, without interruption. And in an office on Earth, the list is already being written again. In November of 2026, Voyager 1 crosses a quiet line. It reaches 1 light day from Earth. Nothing marks the place. There is no boundary out there. No change in the dark. No sign that anything has happened. It is simply a distance, measured in time. Light leaves the spacecraft. It travels for a full day before it arrives here. A day of sunrise and sunset, of traffic and weather and sleep. All of that passes while the signal is still moving. Somewhere inside that gap, people wake up and go to work and come home again. A whole ordinary day fits in there, with room left over. Light is the fastest thing there is, and nothing in the universe is allowed to outrun it. Every distance you have ever crossed was slower than this one, by an amount too large to hold. And now a single spacecraft has pulled so far out that light itself needs a whole day to follow it. That is the shape of the number. It is counted in hours, not in miles. The miles are there too, and they are large. Voyager 1 is more than 15 billion miles away. That is about 25 billion kilometers of empty distance. Voyager 2 is more than 13 billion miles out, roughly 21 billion kilometers, moving away on a path of its own. Numbers like that do not settle anywhere in the mind. They slide off. A day is different. You have spent one, and you spent one yesterday, and the shape of it is already sitting in your body somewhere. You know how long a morning takes to arrive when you are lying awake and waiting for it. That waiting is the length of the new distance, laid end to end across 15 billion miles of empty space. It is no longer something anyone could walk or sail or fly. It is something you can only wait through. There is a way to feel it from the inside. Someone types a short instruction, and it goes out through a dish on the ground, aimed at a point in the sky. The instruction leaves Earth at the speed of light. Then it travels for 24 hours. Through all of that time, the command exists, but nothing has received it. It is a thought in transit. It crosses a stretch of space where there is nothing to hear it. No air, no ear, no machine within a day of light. The spacecraft keeps flying, unaware, moving further away while the message chases it down. After a day, the signal arrives. It is faint beyond any ordinary meaning of faint. It is thinner than the noise of the sky around it. An antenna on a turning planet holds still against all that noise and pulls the thin thing out of it anyway. The spacecraft hears its orders and does what it was told. Then it answers. The answer takes another 24 hours to come home. 2 days between the question and the reply. You ask on a Monday, and you learn on a Wednesday, not because anyone is slow, but because the universe has a speed limit and the distance is real. That is the fastest possible conversation with the farthest thing people have ever made. Everything known about Voyager 1 is a day old at best. Its temperature, its power, its heading, the state of every warm part still working out there. All of it is a memory by the time it lands in an antenna and turns into a number on a screen. The Voyager anyone can see is a version that no longer exists. The real one has already moved on, further out, past the place the signal describes. The delay also changes what a single instruction has to be. Nothing can be corrected in the moment, because there is no shared moment left. Everything has to be right the first time. Instructions go out complete. They are written for a machine that will read them a day from now. The people who write them are aiming at a spacecraft that will not be where they last saw it by the time it reads them. So they aim ahead. They write for a place rather than a moment. The instruction is checked, and then let go, the way you let go of anything you cannot follow. After that, the planet turns under the signal until the hours are used up. The listening happens on a schedule, and the schedule holds. The people who do it have grown used to holding a question in their hands for a whole day before anything comes back to meet it. You plan the next thing while the last thing is still on its way. You learn to think in days instead of seconds. The light day belongs to Voyager 1 alone. It is the father of the two, and it always will be. Voyager 2 is behind it and below it, slower, on a heading of its own. It has its own quieter delay. The two of them left the same planet, weeks apart, from the same coast. They have not been in the same place since. The giant planets bent them onto separate lines, one high and one low, and the lines never came back together. Now they leave along those lines, each carrying a golden record. The gap between them widens every hour. It has been widening since they parted, without a single pause. That has been true for longer than most people have been alive. They are each other's nearest made thing, and nothing will ever bring them closer. They were built in the same rooms, by the same hands, and they will never again be near anything familiar. Each one is alone in a way nothing on Earth has ever been alone. The light day is not a place Voyager 1 arrives at. It is a threshold in the arithmetic, crossed while nothing changes around the spacecraft. The dark ahead looks exactly like the dark behind. The sun is a bright star from out there. One point among many, throwing almost no warmth. Nothing announces the crossing. The spacecraft has no way to know it happened. It simply keeps going. The number moves on Earth, and only on Earth. It is an event in a room full of people, and nowhere else. And the number will not hold still. The light day will not stay exactly a light day for long. Every signal has a little further to travel than the one before it. A day becomes a day and a minute, then a day and an hour, then longer than that. The clock keeps stretching. Nothing out there will slow it down. A conversation that takes 2 days now will take 3, and then 4, and no hand on any dial on Earth will be able to hurry it. Somewhere ahead, the delay passes a week, and then a month, and by then no one alive today will be doing the listening. The instructions will get longer, the answers will get slower, and the work will pass to people who are not born yet. Tonight, both spacecraft are still speaking. Somewhere above you, a signal is on its way in, a day old already, growing weaker as it comes. It left a place where the sun gives no heat. It has been traveling since this hour yesterday. For that whole day it has been falling inward, through country with no name, toward one small patch of a turning planet. It will arrive tomorrow, into a dish, into a machine, into a line of numbers no one will read aloud. The number will say where Voyager was yesterday. That is the best anyone can do now, and it is enough. And somewhere out there, a full day ahead of everything known about it, Voyager 1 is still moving. It is moving now. While you lie here, in a silence, nothing has ever broken. It will still be moving in the morning, further along the same line, with no one anywhere near it. Rest now. Good night.